So today I'm gonna tell you something about a chemical I'm dealing with every day in my work. It's called DHMO, dihydrogen monoxide. I'm just gonna give you some facts about it just to have a little picture in mind. It's the major component of acid rain. It's used in nuclear power plants. There are even some athletes who just use it to improve their performance. If you just inhale it, it might cause sudden death. What's most important is it's not labeled, it's not banned, but it's hazardous. You're all scientists, so I think most of you know what I'm talking about. Dihydrogen monoxide. So I'm just talking about water. And of course it's a main ingredient of acid rain. Every athlete has to use it. You can check it, there are even more facts that are nice to read. Why do I want to talk about water? So I'm a material science engineer, doing my PhD since 2014. I'm actually dealing with what does water and how does water behave in contact to a solid surface. The goal is to kind of prevent some ice to form at this surface, and how do we have to design and how does it has to look like to maybe interact with the water and to make it either freeze later or that the ice cannot actually attach to the surface. I kind of got a little bit fixed on this water thing, and the human body is actually made of 60 to 13% of water, but in the womb we actually start with 95%. So we kind of also just play with water with some carbon inside and some stuff more. Just concerning the chemistry, water is supposed to be gaseous, but because of this high interaction of this polar molecule, so some part of it is more negative than the other one, it's so much interaction that it kind of sticks together that is forming a liquid. And this adhesion or adhesion in between and the surface tension also makes sure then for trees, when some water evaporates, that it actually sucks the water through the stem so that the transport even against gravity. And also in our blood vessels, the interaction between water molecules is awesome. What I learned in one of the presentations in ScienceBeer, that the DNA helix is never there as a single molecule. It's always hydrated by water, and depending on the water amount, it kind of also changes the precise structure of the DNA. There are also some anomalies that we find in water that's not there in most of the other materials. So it actually has the highest density at 4 Celsius degree, and when it's forming the solid state, it actually is less dense. So most materials get even denser when they start to form a solid material instead of the liquid. Not with water. And this is the reason why we can actually have life on Earth, because in a lake there will always be the 4 degrees Celsius water on the bottom of the lake, and the ice will form on top, or it will just swim. So the bottom will stay 4 grad most of the time, or as long as possible, so life can still evolve down there. It was last summer when I met a guy during a birthday party. He was telling me, okay, just do an experiment with water. And I said, yeah, experiment with water. We just take a glass of water, let it sit here with an ice cube in there. And we just talk, go on talking, and this ice cube, when it melts, what happens to the sea level? He was trying to tell me that climate change is not real. So will this level of water rise, sink, or just stay the same when the ice melts? So who's for sinking? Will it be lower in the end? Okay, just one. Will it rise? 4? Will it stay the same? 9, I think. So in the end, we were talking and talking, and I was looking. It was hard to see, but it actually sank a little bit. I was like, oh my god, he's right. Climate change is not real. So what happened? We know the density anomaly, so it jumps down here. It has 0.92 gram per cubic centimeters, and it's 1 gram per cubic centimeter when it's liquid. The force that's actually pushing up ice cube depends on the volume, and the volume that's replaced depends on the weight that needs to be forced up, auftriebskraft. This is ice, the density of 0.92, and this is water with 0.10 gram per centimeter. In the end, this volume of ice will be replaced by water in a liquid state. So if we count the water molecules in there and go with the weight of water that's here, And this weight of water has to be pushed up. The weight of the water molecules, and it's the weight of the molecules that's replaced by this part. So of course, the level will stay the same because of the density change. We'll always believe that 92% of ice is below the water because of the weight of the water that's replaced. And it will push the part that has a lower density, this more volume, it will push us above sea level. So it will stay the same. And what happened during the summer night, we were talking, there was just some evaporation. This was the reason why it actually sank. So now, okay, climate change, it's not happening because the ice that swims and we are safe. The sea level will not rise. But that's actually not true. Because of all the water that's on Earth, there's like 97% that's salt water, of all the ice on there. There's like about 2.1 that's ice. Just the rest is like groundwater and in the rivers, lakes, what we see all day. And of these 2.1 ice, that's not all swimming around. About 1.7% of this is actually on Antarctica, it's in glaciers, it's as snow, so it's actually on land. So when this will melt, and we assume the Earth, when it's evenly spread around Earth, this will have a depth of around 3,070 meters. I did the math, I will not do it in detail, but it will add actually 66 meters when all the ice will melt. So climate change is there, it will rise, and it's actually doing this right now. It's not going to be there tomorrow or in the end of the year, but they say the end of the 21st century, it could be in between 1 and 2 meters already. I already told you some numbers. I want to make another quiz with you. So we have this amount of seawater on Earth. When we now assume we have a glass of water, and it fits like 250 milliliters. What do you think? What number is higher? The amount of glasses of water in like the whole ocean, or actually the amount of water molecules inside one 250 milliliter glass of water? So who is for molecules? Okay, it's almost everybody. I can confirm. So this, if we put all the zeros in there, this is about 5, 10, to the power of 21. This is the glasses of water inside the ocean. So now we need the amount of water molecules in a glass of water. How do we do it? So who knows the Avogadro constant? So now we need to know how much mole of water is in a glass.
More than one.
More than one. You just say, okay, oxygen has an atom number of 16 plus 1 hydrogen. Another hydrogen is about 18 grams per mole. So now we have about 14 moles in one glass, so it's about 10 to the power of 24. 1,000 times more water molecules inside one glass of water than we have glasses of water in the whole saltwater system. I think it's neat. I like this number. Now we already have some imagination of the size of a water molecule and how many water molecules are there. So I will tell you a little bit about homeopathy. I just also want to do some math with it. I mean, I'm just not going to tell you what to do about it. The idea behind homeopathy, you use a substance that usually causes the symptoms you want to cure, and you dilute it with water to make it like less amount. So there's 2 scales. There's a C scale, so it's like 100 times diluted, and there's a D scale. It's just 10 times. So if you have an onicum something D6, it's like 1 part of the substance and 10 or 6 times water. And this guy, he was Samuel Hahnemann, so he was believing he can increase the potency by just diluting it further and further, and he was usually using 30C. So you have 1 part of the substance and you have 10 to the power of 60 of water. So this is actually more than water molecules exist on Earth. The water that's used in a laboratory to do some analysis, if you just have it in the homeopathic notion, it would be a 4C. So we have actually a lot of medicine around us. I mean, I'm not talking about tap water. Just imagine what's tap water. The contamination level. So if you tell this homeopaths, they say, yeah, of course, yeah, this is just maybe 1 molecule inside this whole substance thingy, everything. But there's the memory of water. So the water still remembers that there used to be the substance in there. So this makes the effect of homeopathy.
Every memory?
Yeah.
So
Wait, we already know what's in the water. If we add this, we know how many molecules in 1 water glass and how many water glasses in the whole system. So it's about 10 the power of 46 water molecules there on Earth. So if you drink this glass of water, maybe not once, but you have to drink like 8 times a day, glass of water, and maybe for 100 years. Now that we do some more statistics, maybe it's not possible that you will pick a certain water molecule and put it back into the whole amount of water molecules and get it back one day. But since you're drinking again and again this huge number and you put it back and it gets mixed again, the probability is almost 1 that you will get at least one molecule that's already been through you, so that you drink one molecule twice. So the probability is also almost 1 that you drink a water molecule that's also been through Einstein, or Mahatma Gandhi, or Mutter Teresa, but also Hitler, Stalin, I don't know, Cleopatra. So if those people believe that one molecule of something can transform the information on the water, I do not want to know what information is already inside of my drink. So I rather do not believe the memory effect. Since human Earth or human species is not here on Earth as long as some other species, so that's actually been dinosaurs there for 186 billion years, and they also drank a lot. And they actually could possibly consume all of these molecules at one time in human history, or not in human, but in Earth's history. So I would like to cheer on science with this nice glass of dinosaur piss. All of you, and never stop thinking. Cheers.